I'm going to be presenting to you, it's a collaborative effort between three institutions. So mainly Polytechnique Montreal with the group of François Bertrand, and then University of Alberta with the group of Bob Hayes, and finally the Belgium-based company Umicore with, among other things, a manufacturer of catalytic converters for the automotive industry. And so the work I'm going to be presenting, which is entitled Optimizing the Performances of Engine Exhaust After Treatment System Using Numerical Simulation, it's actually the work of our master degree student, Igor Belot, and supervised by myself, who I am a research associate in the group of François Bertrand. Actually, my background is I have been working for 15 years in the pulp and paper industry, doing numerical modeling. Do not laugh. We use numerical modeling to improve paper. So at some point I thought maybe there are more challenging and important subjects for this planet, so I moved on to Polytechnique Montreal. But paper is a porous media, so my expertise in porous media flow and porous media in general. Okay. So to give you a bit of context, and that I didn't know before starting on this subject. We heard about the scandal about diesel engines that were, and some car companies were cheating on the emissions. So there is an incentive then to going to gasoline, engines. But since 2008, actually the industry have turned to usually the normal gasoline engines were port fuel injection engines. Okay, and the industry has turned to gasoline direct injection engines. So now you're directly injecting into the cylinder the fuel, and that kind of engine is apparently more fuel efficient. Okay? So nowadays, probably 50% of the gasoline engine are GDI engines. The things that I guess most people don't know, at least I didn't know, is that GDI engines produce soot. Okay, and they produce soot in greater number than diesel. I said number. Eh? So if you look in terms of mass, they produce less total mass, but greater number of soot. So it means that the particles are even smaller than the diesel. So in the order of below 100 nanometers. Okay, so they are actually more harmful for the human health and animal health. So to basically avoid this, the industry has designing or putting into his exhaust gas system gasoline particulate filters like we were doing for the diesel engines. And of course, in front of the gasoline particulate filters, you have the three-way catalyst that is used to reduce the NOx, oxidize the CO, and eventually oxidize the unburned fuels. But the industry now is trying to, for many reasons that I'm going to explain, is trying now to delocalize, if you want, the catalysts that are here into the gasoline particulate filters. So combine the two units for, several reasons. Reduce the total number of devices into the exhaust after treatment system, reduce the packaging complexity, lower the overall system costs, and eventually to better remove the small soot particles. So that's the context of this work. So there was also a need from the Umicore company to understand, how the catalyst should be deposited inside the particulate filters, okay, the GPF. Okay, so you have here a particulate filters. Inside you have some kind of monolites, but it's not a real monolite like in the catalytic converter, in the sense that channels that you see here, they are alternatively blocked. Okay, actually we're forcing the flow to go through this cordierite porous wall, which we call cordierite is ceramic, and the order of magnitude of the pore size of this cordierite is in the order of 20 micrometers. And the thickness of the wall is in the order of 30 micron to give you an order of magnitude. Okay? So the idea is to take the catalyst and embed it into the porous media, the ceramic. But of course, they want to do it in the best way possible. So the objectives of Igor's work was to determine the optimal catalyst amounts and eventually best distribution within the pore space. So eventually to have the lowest pressure drop as possible, to have the best soot capture efficiency, to have also the best catalytic effectiveness, and eventually to reduce cost, of course. So we devised a 4-step numerical methodology for the prediction of the 3-way catalyst gasoline particulate filter performance. Okay? So there are 4 steps. I'm going to go in details in the next few slides. So first step is really to reconstruct the porous wall, because we're focusing here only, of course, you could think as modeling the entire GPF, but that will be a multi-scale problem. So for the time being, we're focusing only on the porous wall. So we reconstruct this porous wall using computed tomography images. I have problems here. Okay, so the second step is to compute the flow fields using lattice-Boltzmann method to determine pressure drop or permeability of the porous media. Next step is to compute the aerosol trajectories by solving a Langevin equation to determine the capture efficiency of the porous media. And eventually you can, from the pressure drop and the capture efficiency, you can determine, I'm going to show you later how this factor is devised. It's a filter quality factor, which is independent of the thickness of the filter. And the 4 steps now is to compute the concentration of a species within the porous media and determine the catalytic coating effectiveness and or the conversion of some. So to go into a bit more details, so how do we reconstruct the porous wall? So from 2D tomographic images, of course I won't go into details because this as such is the work of a master degree thesis or a PhD. Okay, we have actually some kind of a German guy working on this full time. Okay, so you have to filter the image. The thresholding, as you know, is quite difficult because here we have to threshold 3 phases: the porous media, the cordierite, and then the catalyst. Okay. So this is not, I have only a few slides, I have only this slide on this, but this is such a big endeavor, okay? So eventually you concatenate those the 2D images and you get the 3D structure. So Umicore provided us with some images, tomographic images of one of the 3-way catalyst GPF converter and filter that they have developed with a certain catalyst deposition inside. And from this image, we are devising, reconstructing several structures where we vary the coat weight, first using a uniform coating deposition, because eventually they wanted to know whether a non-uniform or uniform coating deposition is the best to look for. So to deposit uniform coating layers, we simply remove the catalyst here in white, and then we grow layer by layer the catalysts on the cordierite wall, and then doing so we can have different coat weights onto the cordierite porous wall. Other approach now is to form non-uniform coating profiles at different coat weights. Then we start from the original image. We erode the catalysts and then we reduce the coat weight, or we dilate the catalyst and then we increase the coat weight, and conserving some kind of non-uniformity on the deposition. So the second step, as I told you, is to compute the flow fluid using lattice-Boltzmann method. So I have this slide just in case some of you may not know exactly lattice-Boltzmann method. So lattice-Boltzmann method is relatively, I put it in between brackets because now it has been around for 20 years, relatively new CFD approach. So instead of solving the Navier-Stokes equation, you actually start from the Boltzmann equation, okay? So Navier-Stokes is a continuum mechanics representation at the macro scale of a gas or a fluid. And then the Boltzmann equation, which was devised for gas, is actually applicable for in a certain way for fluids. And it's a statistical mechanics representation of a gas or a fluid. And so it's this mesoscale representation. You start from this Boltzmann equation. Of course, what does this Boltzmann equation? It involves F, which are probability distribution function of finding molecules going in a certain direction from a point time and x in time and space. So you discretize this equation, or don't want to forget to mention here the collision term. This is the collision term. This is the BGK approximation. We heard about that in several talks. This is a relaxation towards local equilibrium. And then we discretize this equation in velocity space. So we get the discrete Boltzmann equation. Then you discretize this discretized equation in time and space using finite difference method. So you get this LBM explicit scheme, which evolved the probability distribution functions of finding particles somewhere in your domain. And this explicit scheme, of course, has some limitation. That is, the Mach number needs to be relatively low, and the Nusselt number needs also to be relatively low. But solving for the probability distribution function, in the end, you can integrate in the velocity space the probability distribution function and recover the density and the momentum, so the velocity. Okay? So that's the approach of the lattice Boltzmann method. And what it needs, is that it has an explicit scheme. So explicit scheme means that it's more efficient in terms of parallelization, so you can, recreate structures that are quite large and parallelize the domain onto, computer clusters. Okay, and the algorithm is also very efficient on CPU and GPU architecture. Other advantages of lattice Boltzmann is that you're actually solving this equation, the Boltzmann equation, on a simple structured grid. So reconstructing any complex domain is quite easy. You just flag cells as being porous or as being solids. And so the phases are encoded in a Boolean manner. So we can, using this method, solve really complex porous media flow. So the third step now is to compute. So having the flow field, you can launch aerosol particles at the inlet of the flow field. And by solving a Langevin equation for each of the particles, you can track the trajectories of the particle and compute the capture efficiency. And again, having the pressure of the capture efficiency, you can evaluate the filter quality. So to go a bit more details, so the Langevin equation is Newton's second law of motion with a Brownian diffusion term. If you want, you can even add thermophoresis term if you need to. The big assumption is that since the soot concentration is relatively low, well, we can use a one-way coupling. So we solve the flow, and we have no coupling between the presence of the aerosols in the flow and the flow itself. Okay, so it's a simplification, but it works relatively well. Okay, so other assumption is that the soot will readily attach to the solid surface as it touches it. Okay. So you see here you have different, so the colors here represent the size of the aerosols, and depending on the size, you see that here the dark blue trajectories are much Brownian than eventually other colors. The porous media would be somewhere here, and this is just the entrance of the porous media. So you see that the red one will actually collide right away at the surface of the porous media. Some will penetrate a bit deeper, and some will fluctuate in front of the porous media and eventually collide on the porous media. So this procedure allows to account for the main capture mechanism for aerosol, which are interception. So interception is the aerosol is following the streamlines, and eventually, because of this discrete size, it will collide to the surface of the collector. You have the inertial impaction term. So because of inertia, eventually the particles will divert from the streamlines and collide with the collector. And you have the Brownian diffusion term, and the combination of all those terms will give you the capture efficiency, the total capture efficiency as a function of soot diameter. So in our study, what I'm going to be reporting, you see I'm going to be reporting the capture efficiency at what we call the MPPS, which is the most penetrating particle size, so the worst case scenario. So the fourth step is to compute the concentration field of a reactant inside the structure. And here also we use lattice Boltzmann methods. Maybe some people don't know, but lattice Boltzmann method has come up from CFD, so from computing fluid flow, so from Navier-Stokes. But actually, it's more than this. It's a PDE solver. Okay, you can use this lattice-Boltzmann approach to actually solve any PDE equation. And here we use it to solve the advection diffusion reaction equation. So in the same way, the solving Navier-Stokes. Okay, of course, well, you need to adapt the equilibrium function and some of the weight of the methods, and you can verify that your approach is actually solving the ring macroscopic equation by doing a Chapman and Scott expansion.
Are you assuming isothermal, like
yes.
feedback? Yeah.
Yeah. So having the flow field, after that you can compute what we call the catalyst coating effectiveness. So you see here you have the concentration field within the catalyst. So the catalyst here you see on this image is in brown, okay? And here you really have the concentration field within the catalyst, okay? And here you have the concentration field within the pore space. We assume here a first order reaction to devise this catalyst coating effectiveness factor. And to calculate it, we simply average the concentration in the catalyst phase divided by the concentration in the pore space. So here, let's move on now to the result part. Okay, these are some of the numerical conditions that we used. So we looked at soot particles in this range. I have to say here, because of the dimension of the geometry, which is quite small, we are in laminar regime. We account for the difference in density of the soot particles depending on their size. And what may sound as a rough approximation is that we consider that there is no soot accumulation. Okay? If we would study diaxial engines or diaxial particular filters, this will be a rough approximation because eventually the soot will accumulate on top of the porous wall structure. But for the gasoline engine, the temperature of the gas is so hot that actually the soot is not accumulated on top of the structure for the most part. Okay, so and here gas is assumed to be isothermal, as you said, and also quasi-incompressible. So this is here an example of simulated flow field in one of the structures that we looked at. So you see here the different phases, catalysts, cordiorite, and pores, okay? You may see on some of my slide wash coat, okay? Wash coat is actually catalyst, okay? You see here the flow fields. This is the permeability that we have computed from this CFD simulation. If you take the Blake-Kosan equation, which does not necessarily apply for this kind of structure, but applies for spherical packed beds, we find a permeability that is quite close. Okay, so that seems to confirm that the code is working properly. And to give you an order of magnitude, it takes roughly 2 hours on 100 cores to simulate this flow field. So here are the results now for the permeability. So let me put some guide for the eye here. So for the uniform wash code, so we have here in red the uniform wash codes. This is here fraction of pore volume filled by the catalyst. So we start from only the cordiorite porous media, and then we fill in the void of the porous media with the catalyst. And then you have permeability. So you see a monotonical decrease as we would expect for the permeability. As more catalyst we fill in the pore space, of course the permeability decreases, which is not surprising. Okay. For the non-uniform wash codes, you see also a decrease. It's not well, it's monotonical, but it's not. This one was a bit quadratic. This one is a bit more complex. You see here the point. Here the black point. It's not an experimental point, but it's the simulation for the real porous media. Okay, that we took, and I recall you that from this real structure we have dilated the catalyst layer, or we have eroded it to create all those structures, and same thing here for the uniform profile. Okay, so this results as such is not so surprising. We see that permeability is decreasing, but it seems that the non-uniform wash codes gets lower pressure drop, okay, than the uniform wash coat. I think we can explain it just by channeling. So channeling allows to not build too much pressure within the structure with respect to, in comparison to the uniform profile. So now if we look at the capture efficiency at the most penetrating particle size, so this is the capture efficiency in percentage, again, as function of the fraction of pore volume filled with the catalyst. So we have here for the uniform profile a monotonic increase that we would expect. And then when Igor brought me this result for the non-uniform profile, I said, are you sure about your calculation? Because this is highly counterintuitive. You fill in the pores with some materials and you capture less soot particles. So he said, well, I'm sure about this result. So I said, well, let's go to see our industrial partners, but I'm afraid he might be suspicious. And when we went into the meeting room, we presented this result. He started to smile. And then I said, two solutions. Either he believed that we are idiots and our simulation is crap, okay? Or they have observed that in the lab. And indeed, he was quite happy to see that this is exactly what they observed in the lab, okay? And they had no explanation why the efficiency was decreasing as we were filling the pores with more catalyst, okay? So I said to Igor, well, return to your data, because what's nice with numerical modeling is that you have all kinds of numbers, you can crush them in many ways. First, he showed that interception was the mechanism that it was the most impacted. So somehow the structure was not capturing the soot particles, but in the end, what turns out to be the most effective way to understand what was happening is just looking at the flow field. So this is here a close-up view of part of the structure. You see the uniform profile wash coats at low coat weight, so you see it's tortuous flow field with a lot of channels, large ones and small ones. When you increase for the uniform wash coat the coat weight, the channels stays more or less the same, only the magnitude of the velocity in the channels increases. Well, that makes sense. When we go to the non-uniform wash coats at low coat weights, more or less the same channeling, okay? But what is really interesting is that when you go to high coat weights, and I'm going to go back and forth for you to look, okay, if my remote is working correctly, you see that at high coat weights, somehow a lot of small channels have been cleaned and been removed, and they participate to the capture efficiency, okay? And most of the flow now goes into large channels, which eventually capture less efficiently than small channels. Okay? So in the end, even if you're filling in the pores, since you're filling it non-uniformly, you're closing some channels, the small ones, and in the end, you decrease the capture efficiency. And you can see it clearly here if we compare the flow fields on the same slide. Okay? You see here it's empty. So having the pressure drop, having the capture efficiency, you can calculate the filter quality factor. ln ln 1 minus the capture efficiency is proportional to the thickness. Delta P is proportional to the thickness. So the quality factor is independent on the thickness of the filter. So it's intrinsic material property and tells you what is the quality of a filter. And if you plot all the profiles that we looked at, basically you get some kind of master curve, okay? And although you capture less with non-uniform profile high coat weights, since its pressure drop is lower, everything basically comes back to the same thing, and there are not more, a non-uniform profile is not less efficient in capturing soot than a uniform one, okay? So for the company, that was quite good news because, of course, getting a uniform profile is very difficult. Okay, so on this side, on the filtering side, this was interesting for them. Okay, but what about now the catalyst's effectiveness? So these are preliminary results. Okay, this is actually Igor sent me that 2 days ago. Okay, so it's very preliminary. Okay, but you see here he has actually programmed himself. Okay, he's a master degree student. Okay, he has programmed himself lattice-Boltzmann code for solving the advection diffusion reaction equation. Okay, he has done intensive verification. This is here the first simulation we do in the real structure. So you see here the concentration field, and by calculating the concentration in the catalyst layer and in the pore space, you can get some kind of catalyst coating effectiveness factor. And he sent me another result, which he has looked already at some structure, and as I think we could have expected, if you have a uniform coating layer, of course, your catalyst conversion should be better than a non-uniform one, and this is what we observe. So even if the non-uniform profile capture suits as good as the uniform one, it performs much less as expected in terms of catalytic conversion. So the upcoming work, so it's to finish this part here a bit about the effect of the Huashko distribution on the catalyst coating effectiveness and conversion. Do experimental validation. So this part will be done at University of Alberta in Bob Hayes' group, okay, and we'll try to validate the different steps of this model. For a long-term, in a long-term perspective, we're going to look at other non-uniform catalysts. Here we started from the non-uniform deposition of the real structure, but eventually we may find other distribution of catalysts that might be better. And for that, we're going to use, we have actually already programmed a simulated annealing reconstruction algorithm that allows us to reconstruct all kind of different catalytic structure inside the particulate filter. And in the end, we want to study the oxygen storage, okay? You see that the reaction process taking place, and these are only a few of reactions that can take place in the catalytic converter, okay? But there is this reaction here, which is called oxygen storage reaction, that helps, to control the sharp emission change that you may have. When you drive, sometimes you speed up a bit, so eventually your fuel is running in the lean regime, okay? So eventually emissions are changing, and this oxygen storage, which use Syria, which is embedded into the catalyst system, is helping in controlling the oxygen inside the system to avoid, big change in the emissions. Okay, so that's another topic that is very important for the company. But of course, that will imply that we need to solve now 10 or more species using lattice Boltzmann. I think it's feasible. How we can do that? By taking advantage of the fact that LBM is quite portable on GPUs. Okay? And we have actually, this is the last slide, we have actually started already to work on the multi-phase color gradient lattice Boltzmann codes that we have implemented very recently onto GPUs that allows us to speed up the computation and compute. Here you see this is flow through static mixers. So this is biphasic flows, okay, liquid, and we can look at interesting phenomena like contact angle and look at the impact of the contact angle on the particle, the bubble size distribution, as well as the relationship between flow rate and pressure drop. This is actually have been presented at the North American Mixing Forum last June. So in conclusion, so far uniform catalyst coating seems to provide a better overall three-way catalyst gasoline particulate filter performance over non-uniform ones. But other catalyst distribution exists. We're going to investigate that. And this is more of a conclusion for industrial people. I think you're all convinced in this room about that. But numerical modeling is a valuable approach that can give insight as to why specific catalyst coatings perform better than others, and provide guidance for the particulate filters manufacturer to improve the performance of their gasoline particulate filters. So let me thank all those organizations and the organizing committee of this workshop for letting me present here. And thank you for your attention. And if you have any question, I will be glad to answer them. This is a flow field. This is a flow field in those porous media. And in white, these are the trajectories of the aerosol. So it looked like a painting. Okay.
Thank you so much. We will take one question while Sean is setting up, and we can take the